Okay. Do you have them?
Mm.
Alright. Oh wait, hang on, I'll turn the light off. It's a bit bright. But I'll open the curtains. Or the blinds, I should say.
Can you talk
Cold. Hey. Better? So, a steam engine. Okay.
is powered by the heat turning coal.
Mm-hmm.
The coal releases
20.
kilojoules of heat during the first second. The 10,000 kilogram train then accelerates from rest up to a speed of 1 meter. What
From rest
to 1?
to 1. And the time? 1, is it? Alright.
Yeah, during the first second.
Okay.
What was the rise in thermal energy of the train?
Good. So, work is force by distance, which is, let's see, S equals UT, oh no, V squared equals U squared, oh no.
Those two
V,
yeah, that's right.
but we don't know the A or the S.
But you only
Yeah, but we don't know the S. We gotta have two things we don't know. It has to be V equals U plus AT. So A is 1. So this is F times 1, which is F, which is MA, which is 10. Oh, sorry, and S equals UT plus a half A T squared. Sorry, so the distance is a half.
yes.
So that's a half. So that's a half. So 10,000 times 1 times a half. So that's 5,000 or 5 kilojoules, which is what you got yesterday, wasn't it? No? But then I'm not finished. So you have Q.
Yeah.
Yeah. Q equals delta U plus W. So delta U is Q minus W, which is 20 minus 5, which is 15 kilojoules. And that's what you got yesterday.
Not with this method.
Oh, that's okay. There's more than one way to do it. Did you get 15,000?
Yeah.
Yeah. Yeah. Okay. Can we do the next one? Yeah. We do the next one, yeah?
Yeah.
Yeah. Okay.
Coal is burned and as such joules of energy is given to a steam engine. The engine produces W joules of work, while at the same time the internal energy of the engine increases by W. The engine warms up. What is the efficiency of this engine?
Good.
But this is that anyway.
Yeah, so it has Q, U, and W in the answer. So, the efficiency, that's the work out over the work in. multiplied by 100. Or power out over power in multiplied by 100. So the work you get out is W, and the work you put in? Q. But we also have this formula that Q equals delta U plus W, so W equals Q minus delta U. So this is Q minus delta U over Q. Yeah, so it's Q over Q minus delta U over Q times 100. So it's 1 minus delta U over Q times 100. Yeah? Now, interesting, I told you that the second law of thermodynamics means that heat travels from hot to cold. But another way to state the second law is that efficiency must be less than 100%. That's another way to actually state the second law. So, if you look here, now, wait. What I'm about to do is not part of the question, it's just an interesting point. So, if you need efficiency to be less than 100%, that means delta U over Q cannot equal 0. Because if it was equal to 0, then you have 100%. So you can't have this equal to 0. Which means, yeah, well, that the delta U can't be 0. So in other words, if you use Q, heat, to make an engine work, you get your work, but you must have a delta U. The temperature must rise of the machine. I just proved it there. This is the proof. Because this is the second law, efficiency must be less than 100%. So that means that delta U must not be 0.
So it's not again.
It's a fact. You can't use heat to make work without making the engine hot. It's a fact.
Even if in the future.
Even in the future, impossible. Impossible, yeah. So the engine must get hot, which means you must use some coolant, like an oil, or, or water to cool the engine down. Yeah. So I just think it's interesting. This is a fact, and because of that, it means this.
Can version like this come in the exam without any?
No, but it's good to know this for physics.
Yeah.
Okay, now you can write it down. Yeah? Okay, now. Let me see how many more lessons we have in this chapter. 5 more to do?
If it's 10, we have 5. If it's 9, we have 4.
Thank you. It's 9. What's this temporary? See, part of me is thinking maybe we could look at some exam questions now.
Yeah, about ideal gas especially.
Yeah. Let me see. Ideal gas law.
Yeah.
Let's see what I have.
It's confusing me.
Really?
I can't not thinking about it. Thinking about it.
Really? My goodness.
Chemistry is much easier.
Of course it is.
Is it?
Here we go. This is a ideal gas law question.
Oil slow PV equal NRC or PV equal N capital KBC.
Nope.
Why?
Boyle is pressure is inversely proportional to volume.
Yeah. PV equal constant.
Yes.
Yeah.
So, do you want to try this and then I can do it? This is a section B question. So you see here you get 11 marks for this ideal gas law question. 11%. It's a lot. So the section B questions in the exam for this year, there were 20 marks a question. Yeah.
There's B6. Yeah. B4. B6.
B6, but I think this year they're only going to go to B5. And you have to do 3, I think. Anyways, will we do this one?
Okay.
Yeah? Do you want to try it first to see if you can do it? Well, you can do the first one, I know. State Boyle's law.
Yeah. Then what is what I said PV equal NRC? What is
Ideal gas law.
Okay. V equals N RT over P.
The first one.
Yeah.
I mean, like the numbers.
Yeah. No. I mean, determine the volume of the container.
Oh, V equals nRT over P. Yeah.
The N will be the kilogram over the relative mass, molecular mass.
Relative, yes.
R 8.31.
8.31, yeah.
The temperature is 10 plus 2,
73,
73.15
yeah.
over the Pascal, 1.5 pounds.
That's it, yeah.
So I don't have to do that calculation.
Okay.
For now.
No, do it now. Don't you have a calculator?
Yeah.
So what?
That's lazy. I don't have to change anything except the pressure.
That's all, yeah. See, it's a nice question. Yes. Oh. I made it.
Morning. Morning.
It's only like 15 or 20 minutes left. Don't worry, I saved the best to last. We did the tutorial on the homework, and we felt like looking at some exam questions. Ms. Sharif wanted to look at some ideal gas law, so we're just doing this question here. Are you finished it?
Number I see.
Okay, great.
The volume will stay the same as I1 because the Pascal is the same as the
No, I think they mean this.
Oh, they changed the Pascal. It's 1.01 and the first is 1.51.
Oh, I see what you mean, because they said it here.
Yeah.
So it's the same as at the start. Yeah.
So if you change the Pascal.
Oh.
The pressure.
Oh, yeah, I see. It's a little different. Yeah.
And the volume will be 0.575. The mass.
Oh, yeah, that doesn't change. Yeah. Finished? Shall we check the answers? Yeah. So, what is Boyle's law?
Pressure is a proportion of the
Inversely proportional to the volume, but you should also say with all other macro state variables held constant. Now let me explain that word there. Iyad or Musharif, do either of you know this word macrostate? Macrostate means
micro.
no, micro means micro. Macrostate variables are pressure, volume, temperature, moles, you know, your PV or N or T variables. So here the pressure has this relationship to volume as long as you keep everything else the same. You don't change the temperature or the mass or anything. The next one is just PV equals nRT. We know the P, don't we? Yeah. We want the V. We can work out the N. It's 0.575 kilograms of oxygen, but it's 32. Now that's 32 grams, of course, not kilograms. So 0.032.
Yeah.
Correct.
How would I know? You assume it's grams.
I thought you did this in chemistry. You always use grams for
Yeah, we did.
yeah.
No, we did.
Well, I think the key word was relative molar mass.
Did you change ever that? We don't change it in chemistry, but it's always grams.
Let's just double check something here. Relative molecular mass. So this is relative to
Carbon 12.
yeah, but is it relative to 1/12 of carbon 12?
It
Should
should be.
be. So it's it's because they used the word relative that they didn't need to put the unit in. Because relative means relative to carbon 12. So what they're saying here is this is 32 times bigger than the mass of 1/12 of carbon 12. No? Yes? Now I'm not 100% sure because chemistry is not my thing. Relative molecular mass. The ratio of the mass of one molecular element to 1/12 of carbon 12. Yeah. So that's why they didn't need the units. Okay. Right, so that's okay. Or is 8.31 and the temperature is 10 plus 273.15, I think. So, just a matter of getting out the calculator. Oh well, I should write down the formula. PV equals N, oh, wrong N, small n. PV equals N or T, so P equals N or T over V. Okay, fraction N, oh my goodness, sorry, N or T. PV over P. Syntax error. 0.28 meters cubed is the answer. Okay. Part 2. Now, did you get that, Musharif? Did you use 32? Okay. Part 2. The volume changes. What's the new volume if the pressure changes? Now, what's great here, there are two ways to do this. The only thing that changes is the pressure goes from its value of 1.51 times 10 to the 5 to 2.51 times 10 to the 5. So if you wanted to, you could just use this formula again, except change the pressure. So if I just backspace, change that 1 to 2.
No.
What do you mean no?
Yeah.
0.168. That's pretty sweet for another 3 marks. You've got 6 marks by using the same formula twice. Pretty sweet. But there is another way to do it. If you look at how 1.51 times 10 to the 5 increased to 2.51, that has become 2.51 over 1.51 times bigger. It's become about 66% bigger. If you want to think about it like this, the volume has been the pressure has been multiplied by 1.66. So there is a law that says pressure and volume, they're inversely related. In fact, that was the very first law, Boyle's law. So if the pressure increases by this much, then the volume should decrease by the same amount. So a decrease means you multiply it by 1.51 over 2.51, or in other words, multiplied by 1 over 1.66. So we should get the exact same answer. So let me just flip this around and multiply it by 0.28. Exactly the same answer. So by Boyle's law as well, you get 0.168 meters cubed. So you have 2 ways to do this one. Yeah. And the last part here, what's the density? And density is mass over volume. The mass was given as 0.575. Now, the volume, we'll have to work it out. Again, you have to work it out. It's not quite given. Remember, PV equals N or T. So volume is N or T over P. Actually, it sounds familiar. Didn't I say that already? The pressure. Yeah, so we have to work it out. In fact, it's a third volume now because it's now a different pressure. So it's even a third volume. Yeah. So P N or T over P, or if you prefer to make it a little bit neater, that times P over N or T. Now the good thing is we're given the P, it's 1.01 times 10 to the 5. We have the N from earlier, it's 0.575 over 0.032. We know the R, of course, and the T is 273.15. Yeah? Yeah, no, what were you thinking, Ian?
No, I just thought the end was 0.575, but then I saw that
Yeah.
divide the area.
Syntax error. Syntax error. I missed a multiply or something somewhere. No. Oh, my brackets. $1.42. That seems awfully small to me. Is that what you got?
Yeah.
Well, you know what? I have the internet open. I can easily check the density of oxygen. 1.423 kilograms per meter cubed. Oh no, I closed the internet browser. I'll open it again. Okay. I think that one's okay, isn't it? We could do another question. Thermodynamics. Do I have a thermodynamics question for you in this paper? What do you mean by thermodynamics? Yes, I do have that, but I need to think about which year it was. I think it was a while ago. Let me just have a quick look here. And let me just check up the density of oxygen at standard temperature and pressure. 1.428?
Yeah. That's awesome, good.
Awesome. There is one. I'll find it in 1 minute. Or maybe I won't. Don't know, Miss Sharif. Don't know.
Then,
No. It's good to be prepared for anything. Oh, I found it.
explain briefly concept.
Now this is exactly what I was talking about. Remember that proof we did of what was it, PV equals 2/3E? This one says, explain briefly how the molecules of gas can exert a pressure on the wall. That was part of the proof. So they never ask you for the full proof, but they do test you understand it. See what I mean? Now, how did the molecules create pressure on the wall? So what happened was, when the molecule hits the wall and comes back, you have the formula change in momentum. Let's say this is mv, and then when it comes back it's minus mv. So change in momentum is mv minus mv.
2mv.
Yeah, which is 2mv. Then you divide it by time. Yeah. Then this is equal to force. But force divided by area is pressure. Let me just put an A in here. Times A times A. So you get, therefore, pressure is equal to 2mv over area times delta T. So the pressure is caused by the mass of the molecule and how fast it hits the wall. And also the area of the wall and the time here. Now you could explain this in a paragraph, but for me, I prefer to explain things like this. So, not only have I explained why the molecule creates pressure on the wall, I've actually calculated how much pressure is caused by a molecule of mass m with velocity v hitting the wall of area A during a process of time t. So, I hope, Sharif, that proves to you the importance of the proof. No? This is an important one, especially for Musharif, so I better write down the year. This was 2007 to 2008, version 4, B3A. Yeah.
So this is the third proof that we need?
No, but it's not really a proof, you see, because it's incomplete. It was only part of it.
No, you said in this course we have 3 proofs.
Yes, that's right, yeah.
This is the third one?
No, this isn't a proof. Sorry, Musharif, when I said 3 proofs, what I mean is there's 3 proofs which you'll need to fully remember and write in the exam. Do you know what I mean?
Yeah.
So, do you remember the 3 proofs?
2.
2 proofs. What 2?
Time graph.
The time graph?
Yeah, the tau.
Yeah.
Plane.
Yeah.
Yes.
And the UVA here.
Yes. Yes. The third one is Kepler's second law, which we haven't done yet.
V here is velocity, correct?
Yeah. Yeah.
So I just have to
Don't ask
explain
me.
in words. Just this.
Yeah, it depends what you prefer.
Four.
This isn't a proof.
This is
It's not really a proof. Because you could, because you could have written a sentence. You could have said something like this: the pressure on the wall is caused by the molecule impacting the wall and changing its momentum, thus causing a force, thus causing a pressure. You could have said that. That's not a proof. Right, let's have a look. I think there's another part to this. Now, do you remember this one? In the proof,
Yeah.
I said there's some important features of an ideal gas. Do you remember what they are?
Low density.
Low density was one.
No intensity.
Ignoring gravity, or I think they might have said ignoring a force. Because not just gravity, but use gravity usually, yeah. Anything else?
Acceleration. Ignoring acceleration, I think.
No, the other one is you treat the ideal gas as just colliding molecules, like balls bouncing off of each other. There's nothing special. They just like collide and bounce.
With no acceleration between them and colliding molecules.
Yes. No acceleration between them, or no interaction?
Attraction.
Attraction.
Oh, yeah.
That's different. Okay. Right. The pressure of an ideal gas is given by this formula, 1/3. Now this is actually a new formula. 1/3 density c squared. Explain what c squared means. Now they're trying to trick you here. I didn't quite like that they did this. Not trying to trick you, but pressure equals 1/3 density, and then they write this here. Now think about some formulas you know. You know PV equals nRT. I think we also did PV equals 3/2E, and there was another one as well.
P equals density Hg.
No, not that one. Another one.
For P?
That had PV in it.
Only N capital K.
No, there's another one. Yeah, there was.
Do you remember?
No, alright, well maybe I'm imagining it. Anyways, we have to kind of work out what this symbol means. Now if you had no idea, you can just look at the units. So what's the units for pressure? Now I know what this means, and the hint is these brackets. Do you remember what this means? Average. And this is a square, so we're thinking maybe it's like average velocity squared. The average speed of the molecule squared. Now, if you're not sure, no problem. What's the unit for Pascal? Yeah, Newton per meter squared. And density? Kilogram per meter cubed. And this we don't know. Yeah. We can cancel that with that. Yeah, the two of those. So we get Nm over kg equals the units we want. Now, we need to clean this up to try and figure out what it is. So Newton, you might remember F equals ma. So a Newton is a kilogram meter per second squared. So this is kilogram meter per second squared, meter over kilogram. Kilograms cancel, so you end up with meter squared per second squared equals the units. Or in other words, you get meter squared over second squared equals the units. Or in other words, meters over second squared equals the units. So it's velocity squared. So in other words, this C must be a velocity. So the only thing it could be for the gas is the average velocity squared of each, the average of each velocity squared. So I think the reason they put the C instead of a V is not to make it too obvious, to make you think a little bit about it. Because, you know, it's 1 mark. Yeah. Yeah. Well, I only did this for you to see it. I knew it was velocity, so, you know, if I was doing the exam, I would just write down velocity. But we better be careful. I'll write it down here. The average of the squared velocity of the molecules. That would do it. I like the materials question in the exam. I don't feel like it's too hard. Especially the ideal gas law questions. Because you do them in chemistry, so you should be quite expert at doing them now. Do you do Boyle's law in chemistry? No? Just ideal gas law? Okay. Can I close this? Oh, come on. If they ever ask you what's a thing in a formula and you don't know what the thing is, looking at the units can give you a hint on what it is. Yep. Okay. And the last part we can, we don't have to worry too much about. They give us the density. They give us the pressure. And they want the C here. So maybe I won't fully do it, but I'll just do a bit of it. Pressure equals 1/3 density times average velocity squared. They want this. They give us this, but they don't tell us this. But they also tell us the temperature.
They want the pressure.
Oh no, I'm sorry. They do give us the pressure.
And density.
Okay, then.
They give us the pressure.
Straightforward.
No, they don't give us the density.
Oh, okay. We have a math.
Do we?
No.
It's weird. They give the pressure in these units. Oh no,
No, that's
I'm misreading it. The density is this.
Yes.
So we're given the density and we're given the pressure. Goodness. So all you have to do is just put in 3p over the density. Oh sure, we might as well do that now. What did it say the pressure was? 3 atmospheres. And then divided by 1.4.
Half the pressure
Is okay? Uh, 216,000. Now the reason it's so big is because it's the velocity squared is what they were looking for. So that's equal to 216,000 meters per second squared. Yeah.
we multiply the 3 by the pressure.
Yep. And divide by the density. Actually, that's a very easy question. That's why it's only 2 marks. Okay, we'll wrap it up there.
Can you come?
No, there's a class right now. What? Yes?
Calculate the
Oh.
R and N.
Yes?
They say the answer of the I3. Calculate the R and N.
Yeah?
The answer for the what is C?
Huh?
You know I3?
Yeah?
The one is for 1 mark.
Yeah, explain what it represents.
And look at the IV.
Yeah, calculate the RMS velocity. Yeah.
Yeah, the answer is in the question.
I know, but the problem is they said RMS, they didn't tell you. I know, no, I get what you're saying. I remember saying this last year to the students, but the problem is you don't know what RMS means. But you're right, if you read the next part, you would have even more of a hint that it's the velocity. Now, we better go.